So I should preface by saying that this week we have a bit of a challenge in that we have 2 days worth of material that we have to cover over 3 days. So we're going to take our time. Going to stroll a bit here. And so since I realized that, wow, we have time, I thought, why don't we go do those problems? So we'll do some physics types problems. Now these problems, they're from the book, are very similar to problems from the book. And they're not too difficult, I hope. But I think it's good to get into sort of the habit of doing problems and also thinking about things. We might be a little bit rusty. May have been a long summer where we didn't do enough math every morning. We woke up and maybe said, well, I'll skip my math problem today. So it's good to get back into the habit of doing this. All right. So our first problem. And we talked a little bit about this last time. So there's a spacecraft which is heading to the surface of a small moon. So small, we can't ignore its gravity. Now you might be thinking, that's no moon. But, well, it's a small moon. All right. And it's traveling at 1,000 miles per hour. And it's going to slow down. And it has rockets, which can slow it down at a constant rate of 20,000 miles per hour squared. And the question, at what height above the small moon should the rocket start to fire to ensure a soft touchdown? All right. And we talked about this last time, where the idea is, okay, here's our surface where we're trying to land. And we have our rocket. And so our rocket is going to be up here, coming down. Well, I really should say our spaceship, and it's going to fire its rockets. And we want to fire it in such a way that it comes and it lands softly. And one of the things we said is, what does it mean to be a soft landing? Well, we know what a hard landing is. A hard landing is when you add a little bit more to the moon. And so that would be if we were traveling too fast when we hit the surface. Now, no landing is, whoops, we fired too early, and our rockets stop us before we get to the surface and then shoot us back up into space. So the soft landing, the key here is that we want our velocity to be 0 when we touch down. That's the idea of what a soft landing is. All right. So let's start digging into this. Now, one of the first things we do is we want to make sure we understand what things mean. So we talked about the soft touchdown, but also I see this as a math problem, and I see numbers. So I like to think about the numbers. What about this number, 1,000 miles per hour? How am I thinking about this number? What is that? Yeah, it's an initial velocity. Now, it's not the velocity at all times, but it's an initial velocity, and we should really think about, when we say the initial velocity, it's really a velocity that's happening until we turn on the rocket. So really we're thinking about the rockets as being the start of this problem. So that's how fast we're traveling when we turn on the rockets. We'll think of that as our initial velocity. Now I like to follow a lot of convention, just says V0. And usually we put 0 there to be the initial, or maybe at times 0. Okay, equals 1,000. Is that right? Units sound like a physics thing. We're math. We're purists here. We don't need units. Well, I could put miles per hour, but there's something. You might notice I've left a suspicious gap. Negative. Why negative? It's going down, right? Because we're thinking about this spaceship in relationship to the surface. So when we think about it, is it getting close to the surface or far from the surface? If it's getting close, then we need our velocity to be negative, because that's an indication that something is shrinking. We're decreasing distance. Velocity positive would be increasing distance. So that's why we need a negative velocity. Okay, good. Now, there's another number here, 20,000. All right. What is that? Acceleration. Now, is that the initial acceleration? Constant acceleration? Constant, yeah. So we can write acceleration. There's no like subscript here because it's always the same acceleration, is 20,000. Okay, is that right? I mean, there's a suspicious gap here. Yeah, we can put a plus sign. Yeah. Okay, now we should make sure this agrees with the logic. Should acceleration be positive? Well, think about it in relationship to velocity. What is it we're trying to do to velocity? We want to get it to 0, which means we really want the velocity to go from a large negative to 0. So our acceleration should be positive because that is what's going to get it up to 0. All right. Now, a lot of this comes down to how you orient things and label things. So if you choose different orientations and different labelings, then you can change the signs. But okay. Now, I could have written, instead of acceleration, I really could have said acceleration as a function of time. So it's not like there's a constant called acceleration. It's like at every time there's this acceleration here. Now, we keep working. Well, where are we going? Well, we're going for a distance because it asks us a height. So we got to somehow start with the function, and we only have one function right now, the acceleration, and get somehow to distance. So what do we do? Okay, we integrate. If you integrate acceleration, what do you get? You get velocity, all right? So what is velocity? So what's the integral of 20,000? 20,000 t. Anything else? Okay. So I'll say plus a constant c. And some people said, hey, that c corresponds to what's happening at time 0, because if you plug 0 in, you just get the c, the constant. Okay. So using our information, we can say, okay, this is how our velocity is behaving. It's behaving as 20,000 times t minus 1,000. And there we go. All right. We've made progress. Okay. Now what? Integrate again? All right. I mean, it's a technique so nice, we should do it twice. Integral of velocity is position, which I think uses s. Okay, so what's the integral of this function? 10,000 t squared minus 1,000 t plus a constant. Now I shouldn't use c because I've already used c. So I'll move up to the next letter of the alphabet, d. Now don't worry. As the semester goes on, we'll really get to explore the alphabet. We'll sometimes have problems where there's like 9 constants we have to figure out. So we'll get all the letters involved. Alphabet soup. It's very exciting. Good stuff to look forward to. All right. So what is it we're after? We want to know at what height we should fire the rockets. How do we find that information? Now someone said it's D, right? Well, what do you mean by it's D? D here is your starting position above the ground. Okay, so that's what we want. You plugged in time 0. Aha! So we have the answer. It's D. We're just D miles above the surface. That's when we fire. Good. Oh wait, that probably won't get us full credit. Okay. So, what do we do?
Don't you need to plug in and find where velocity equals 0?
Okay, so we don't have enough information. So we do have to figure something out. We do know that we wrote down velocity equals 0. So probably at some point in time we should talk about velocity equals 0. So that seems like a reasonable thing to do. All right. So if we set velocity equals 0, That's the same as saying that 20,000 times t minus 1,000 equals 0, or we could say 20,000 t equals 1,000. Well, there's a lot of zeros there. Okay, the good thing is it's really easy to cancel zeros. So every time you cancel a 0, it's like dividing by a 10. So we could say, if we cancel off the lots of zeros, we could say that 20 times t equals 1, or what would t be? 1 over 20. Now that might not sound like a lot of time, but keep in mind, what are our measurements of time here? Hours. So this is 1/20th of an hour is 3 minutes. Okay, that's not so bad. If it had been seconds, so like, wow, that's a thrilling 1/20th of a second. All right, so time is 1/20th. So we know that says that we want it so that at time 1/20th our velocity is 0. Okay, so how does that help us?
Set it equal to 0 and the position.
Set what equals 0?
You set your position equation equal to 0
At what time?
at time.
Yeah. See, so we know that velocity equals 0 when we touch down. So that says that, aha, we can even say, aha, t is 1/20th at the touchdown. And so we can take that and plug it in. All right. So we have, do it up here, s of 1/20th should equal 0. Okay, so we get, that's 10,000. I'll count the zeros there. Times 1 over 20 squared minus 1,000 times 1 over 20 plus d. Okay, well, what's 1,000 divided by 20? 50. It's not so bad if you think of just cancel some zeros first. It's the same as 100 divided by 2. Okay, so 50. There's a minus. All right, 10,000 divided by 20 squared. 25. You can think of divide by 2 zeros, right? Because there's 20 squared, so that knock off 2 zeros. And then 2 squared is 4, so it's really like 100 divided by 4. Okay, so this is 25. So 25 minus 50 plus this value d should be equal 0. What does that tell us about d? D needs to be 25. 25 what? Miles. Someone earlier said, you needed the units. Mathematicians know the units always work out at the end. So whatever it should be, that's what the units at the end. We save our units for them. So 25 miles. There we go. There we go. Okay, good. Any questions on this one? All right. Looks like we're good on this one. So let's try another one. This one's taken directly from the text. So a little bit action-packed here. A bomb is dropped from a helicopter hovering at an altitude of 800 feet above the ground. From the ground directly beneath the helicopter, a projectile is fired straight toward the bomb, exactly 2 seconds after the bomb is released. With what initial velocity should the projectile be fired in order to hit the bomb at an altitude of exactly 400 feet? All right. Feels like there's a lot going on. Let's draw some pictures here to help us understand. Because it's good to sort of make sure we understand the sequence of events as they unfold. So initially, we say, okay, well look, there's a helicopter. So we'll draw ourselves a little helicopter. There's our helicopter. And it's pretty high up. So we can say, all right, it's 800 feet. And we'll time, well, let's say at time 0. All right. And at that time, a bomb is released. So there's a bomb, and it's, let's go. What happens to that bomb after it gets released by the helicopter? Just starts falling. You might even say that it's free falling, right? Yeah. All right. What's the next interesting event in our story here? Yeah. 2 seconds later. Time equals 2. That they say, hey, we're going to fire something up towards the bomb. A projectile of some sort. Say, okay, so that's going to be fired from the ground. Now, what's happened to the bomb in the intervening 2 seconds? It's still falling. So it's moved down a little bit. All right. It's gained a little bit of speed as it's moved down. And what's the next interesting event? Yeah. So the next interesting event is that at 400 feet, halfway, we see that the bomb and this projectile are going to collide. Now, so at this point, the bomb's going to be falling a lot faster than it was just a moment ago. And, all right, and the projectile, okay, that's moving up. Okay, and they collide. Good. So now we have sort of the story here. All right. So our goal is, well, how fast do we have to have this projectile go up so that this is the sequence of events? By the way, what time is this? We don't know yet, but we will. We will. All right. So we have 2 things in play. Where should we start? Should we start with the bomb or the projectile? Start with the bomb. All right. All right. I guess there's still a projectile here. It just hasn't been fired yet. Okay. So let's start with that. What do we know about it? Okay, so we know when it comes to the bomb that it has a couple of things. The initial velocity is 0. What are some other things we know about it? So what is the position? Okay, initial position is 800. Anything else? Acceleration, do we know the acceleration? Gravity, do we know what it is? There's a lot of discussion going on about how much gravity there is. You know. Let's assume it's on Earth. Now, some people are like, well, 9.6 something, right? Is that what we should be talking about? And why not? Because it's in feet. 9.6 is meters. Is it 9.8? Okay. Well, that's why I teach math. So what is it in feet? 32.15. Or 32. Again, I teach math. Okay, so acceleration is 32. Now, wait, is it 32? Negative 32, okay. Now I'm wondering, is it 0 or negative 0? No, just 0. Now, when I say acceleration here, that's not an initial acceleration. That's just always the acceleration. So we can say, okay, so we have the acceleration function is negative 32. All right, well, let's build up here. What's the velocity function? Negative 32t, and then what would happen? Plus c, but the c would be the initial velocity, and we know something about the initial velocity. And so we can say, really, our velocity function is really negative 32t. Okay, so there's velocity. Now what? Position function. Okay, what's our position function? Negative 16t squared plus another constant. Now we've already used c, so we should move up in our alphabet. Okay. The constant, the next one is d. Do we have enough information to solve for d? Yeah, what is it? It's 800. Because at time 0, when we release it, we're at position 800 above the ground. So we say, wonderful. So our position is minus 16t squared plus 800. Now, is there any new information that now that we have the position function, we can gain? Plug in 2. If we plug in 2, what will we have? We'll find the position where the bomb is at time 2, but do we know where the position of the bomb is at time 2? No. But we could find it now. But does it help us? Yes?
We should find what time it is when the bomb reaches 400 feet.
Okay, so what does that give us? So if we know where the bomb is at time 400, we know that. So we can use the information about where the bomb is when it's at a height of 400 to figure out when the collision between the projectile and bomb occur. All right, so that sounds like a good plan. Okay, so if we set 400, that's equal to minus 16t squared plus 800. All right, well, we can move stuff around here. Move the 400 to one side, move the 16t squared to their side. Let's see, we get 16t squared, carry the 7, move the 3. That looks like a 400. Okay. 400 divided by 16. 25, yeah, good. All right, good. T squared is 25. T equals 5. Now someone might be like, or negative 5? No, 5. 5. We're moving forward in the story. We don't push rewind here. T equals 5. So now we know when the collision occurs. So 3 seconds after we fire that projectile, that's when we're going to hit. Okay, great. Great. I feel like we've learned something. Good. So are we done? How do we know? Yeah, see, you always need to remember, what is it you're looking for? And you're not done until you found that. So, but it feels good. It feels like we're closer. Okay, so I think we've extracted as much information as we can from the bomb's perspective. So let's move to the projectile. All right. So, great. Now here things get a little bit, but okay, we can handle. We'll have a conversation in a moment. What are some things we can say about our projectile? What's the acceleration on it? How about that? We'll start there. Yeah, it's still negative 32. Just gravity. Okay. So what's the velocity look like? Minus 32t and plus a constant. Okay. What's position look like? I think 16 squared plus and E times T plus F. All right. Now, at this point, you're probably like, ugh, Steve, we should know these numbers. Come on. Okay. Is it? Is it? Is it? No, it's not. Okay, so there's a suggestion here that F should be 0. I've said it's not. And I have a room full of people that say, Steve, you're wrong. Why is it not? And then how do we change it so that it is? When are we at height 0? At time 2. That's when the projectile fires. Now, if it was at time 0, then F would be 0, and life would be good. So what can we do? Well, there's a couple of solutions. We just accept, okay, at time 2, we're at height 0. So one way we could approach this problem, we could say at time 2, we're at height 0. And at time 5, we're at height where? 400. That leads to 2 equations. What, plug in time 2 equals 0. Plug in time 5 equals 400. 2 equations, 2 unknowns. Okay, we can do that. We can do that. Or we can do something else. And here's the something else. Let's just change time. We'll re-index time from the projectile's perspective and say, hey, from my perspective, if I'm the projectile, I really don't consider anything happening until I light up. So I'm going to call that my time. So I'm using capital T. I'm re-indexing time. Now you might be, are we allowed to do that? Apparently, because I just did. But this happens in physics, where they say, oh, just change your perspective. Where is 0? Relabel, re-index. If you can do that with position, you can do it with time. It's okay. And so now what we'll do is we'll just go through and put some capital T's in here. And if we put in some capital T's, then that makes life a little bit easier. All right. So now S at, if I use my capital times 0, what's my height? 0. Now things are easier, and if I plug 0 here, 0, 0, F. Ah, good. Yes, what we wanted. Okay, so we can now say our position function looks like negative 16 capital T squared plus our E times capital T. Okay, now what do we do? So yeah, plug in time 3, set equal to 400. So 400 equals negative 16 times 3 squared plus E times 3. Okay, 16 times 9. What is it?
288.
No? 144. 144. Now you might be thinking, ugh, gross. Yes, it is. 144 is 1 gross. So a gross is a dozen, which is, okay. All right, a little bit of math humor. Very small. All right, so we get negative 144. Move it across. 544 is 3 times E. All right, so what does that tell us about E? 544 over 3, also known as? Exactly, 544 over 3. 3 doesn't go into 544. Okay, now, what is it we want, though? We want our initial velocity. Okay, how do we find that? You plug 0 into velocity. But, aha, because we've re-indexed time, that means you plug 0 in and you get E out. So what's this? It's our answer. It's our initial velocity. And of course, because we're a physicist at in this problem, we write down, oh, it's feet per second, because it was always that way. Of course we were doing our units. But we see, oh, it said the word feet, and like, oh, it said the word second, so it must be feet per second. So we're good. We're good. And there you go. I think this problem can look intimidating when you first see it, because it feels like there's a lot going on. But if you break it down and just think about, okay, think about the parts. Think about how it all fits together. No single computation was very hard. It's just a matter of saying, okay, how do things fit together? And then when you see that, it's okay. It's not so bad. Any questions on this one? You feel good about it? All right, good. So let's go to a different topic. And this, I don't want you to get too hung up on this. So I'm calling this a background fact. In the book, they call this Theorem 1, I think. But this, it's just, the idea for this is to say, there's this idea that solving differential equations is hard. Now you're probably thinking, it hasn't been so far, we've always solved it, or we always had this black box, but the black box doesn't solve everything. It's very easy to get stuck. So one of the questions that we often have is, well, is there even a solution out there? And if there is, how many? We'd like there to be just one. And so this is a nice fact that helps us to say, yeah, there is a unique solution out there if we're dealing with something nice. And a lot of the time we will be dealing with something nice. So this is just, what do we mean by a nice thing? So here's the setup. We have a differential equation. So this is a first order differential equation, which means we can think of it as the derivative that we're looking for. We're looking for y. We want that function y. And the derivative of that has some expression involving x and y. So when you see that f of x and y, just think of it, it's some expression which involves x and y. So there's our differential equation. And there's some initial condition. Y of a equals b, which means that when we plug in x equals a, out we get y equals b. All right. So there's two important points here. The first point, if our function, so this function f of xy is continuous. Okay, let's pause for a second. What do we mean when we say something is a continuous function? What do we mean by that? What do you think of continuity? Okay, no holes, no asymptotes. What else? Well, differentiation is actually a little bit stronger than continuity. You can be continuous without being able to take a derivative. Sharp corners are okay. So like the absolute value has a sharp corner. And that's a continuous function.
The limit on both sides has to be the same?
Limits have to agree. That's almost right. So people mentioned the word holes. They mentioned the word asymptotes. Another thing is you can't jump. You have to, pew! That's bad. Here's how I think of continuity. No surprises. What you think should happen is what happens. Like if you have a hole, you're like, I don't think there should be a hole. There's a hole. Or you're like, I don't think there should be a jump. There's a jump. That like changes what you think should happen. All of a sudden you're way up where you thought you should be. So continuous just says no surprises, no surprises. Okay, so if you have a continuous function, where you're interested in, and where you're interested in is your initial conditions. X equals a, y equals b. Something exists. There is at least one solution. All right. Now, when we say it exists nearby. It doesn't necessarily have to exist for all values for x, but for x nearby. But we just say, look, at least there's something out there for us to find. So the first thing is if we're continuous. The second point says if you're even better than continuous. Okay, so what is the better than continuous? You have this thing. It looks a lot like a derivative because it's a derivative. So that's a good reason why it looks like a derivative. It vaguely looks like kind of like a df dy. And you should think of it that way. It says take the derivative of f with respect to y. So notice that our function, it depends on two different things. It depends on x and y. And when you see this notation here, it says, don't worry about the x. X can do its own thing. take the derivative of just the y part and see what that's doing. So, if this function is continuous, then the solution is unique. So, if you have a reasonable function, if it's continuous, there exists a solution. If it's also nice in that you can take a derivative, that solution is unique. And that's the background fact. And most of the time when we deal with differential equations, y prime equals f of xy, we'll see that these are relatively easy functions to deal with, and they are continuous, they are differentiable in many cases. So we know that there is a unique solution nearby. Now, there's a note on the bottom here. It says, look, there might be other limiting factors which constrain. In other words, we really can only say something is happening nearby. It doesn't mean it has to work for everything. It can work in some interval. You say, okay, well why does it have some interval? So this goes back to an example very similar to what we talked about previously. Look at this differential equation. Y prime equals y squared. Is y squared a continuous function? Yeah, it's not surprising at all. None of us are like, oh, y squared? What? No. It's fine. It's a nice function. What's the derivative of y squared? Is that a nice function? Yeah. So this says, look, there is a solution. It's a unique solution. And it doesn't matter what choice for y or x you plug in. There's always going to be a unique solution because it's just such a nice function. Y prime equals y squared. Now, what does it look like? Well, if you do it, and we did this previously, it looks like 1 over 1 minus x. And you can check. Plug in 0, you get 1. Okay, that says initial condition is satisfied. Take the derivative of 1 over 1 minus x, you'll get 1 over 1 minus x squared. So the derivative is the square of the function you start with. They're both easy to check, namely the initial condition and the differential equation. But what does this function look like? 1 over 1 minus x. Have you never seen 1 over 1 minus x before? You can think of it as it looks like 1 minus x, but turned upside down, right, Steve? Okay. It has an asymptote. How about that? Where's the asymptote at? Okay, good. 1. Okay, and if you plot this function, it will look something like the following. Let me choose a decent color here. It comes up, and then it goes up from below. And our initial condition is right here. So the claim is there is a solution, and there's one solution. And it's this curve, 1 over 1 minus x. But the question is, where is the solution valid? Do you remember we had a conversation? I know it was a long time ago, like 3 days ago. A lot happens in 3 days. What? Yeah. So this solution is valid for x less than 1. Now, you might say, but wait a second, Steve. I see this function 1 over 1 minus x. It's valid for every x not equal to 1. Why do you claim that this part on the right-hand side, to the right of the asymptote, why is that not part of the solution? So the problem is you can't continue. Because when we talk about a differential equation, it says you have to start someplace. So we start at our initial condition. And then the y prime tells you how to move. So we can move along it using the information about how we should change. But in order for me to be part of the solution, I have to be able to start at my initial condition and move along the curve without leaving it. I cannot get from one side of the asymptote to the other without leaving the curve. and starting again. So I'm not able to transmit information past the asymptote. So that's why it's only valid for x below 1. So this comes into why we have these little phrases nearby. Because it says, look, things can happen as you move away from your initial conditions. Things like asymptotes, which restrict the solution. Okay. Now, let's see if we learned. Here we have a bunch of initial value problems. I should probably learn how to pluralize things. Problems. There we go. Use the fact. So the fact is what's on the left-hand side. Use the fact to decide when a solution and or uniqueness is guaranteed. So in other words, what does the fact tell us about whether a solution exists? Does it have at least one? And does it tell us it's a unique one? All right. So our goal is to understand the fact. So let's start. See how far we get. Y prime equals 2x cubed plus y squared. So our function, this part here, this is our f of xy. What we're after is trying to say, is this a nice function? And it's continuous, and if we take it with respect to y, is that continuous? So what is about this function? Is it nice? Is this a continuous function? Yeah, this is a nice function. This is the kind of function that you would take home to meet your family. They would say, oh, what a lovely function you met in college. I'm so glad we sent you to a good university. All right. What about the derivative of this function? Is it still nice? What is the derivative of 2x cubed plus y squared? Be careful here. We're taking the derivative with respect to what? Just with respect to y. So what happens to the 2x cubed part? It goes away. We treat it like a constant. So the derivative would be 2y. But again, that's a nice function, right? Yeah, so does a solution exist? Yes. Is it unique? Yeah, because the derivative is nice. Okay. All right. Next one. Y prime, which is the square root of x minus y. So this square root of x minus y, that's our function. Our initial condition says when x equals 3, y should be 2. Does a solution exist? Is this function continuous? Where? Well, let's think about it. X equals 3, y equals minus 2. What can we say about x minus y? But what is it? 3 and negative 2. What does x minus y? 5. So if I'm near x equals 3 and near y equals negative 2, this is near 5. Is the square root continuous if I'm near 5? Yes. So does a solution exist? Yes. Is it unique? What does the derivative of the square root function look like? Roughly speaking.
1 over the square root.
It looks like 1 over the square root, right? There's a half that comes into play. There's a little bit of chain rule on the inside. But basically, it's like 1 over the square root, for all intents and purposes. And remember, the square root part is near, the inside of that is near 5. And is my derivative okay? It is. Yeah. It's still a continuous function. All right, good. We're racking up the yeses. Okay, the next one. Y prime equals the square root of x minus 1, y of 1 equals 1. Oh, we just did this differential equation, right? What's different? Initial values. Okay, so this x minus y that we're plugging into the square root, what are we close to? 0. Is the square root continuous near 0? No. It's not. Now, here's the thing. If you're not continuous, forget differentiable. So if exist is no, unique is an automatic no. You can't take a derivative if you're not continuous. Forget it. Hopeless. Hopeless. All right. The next one. Y prime equals 4x minus 4. Well, that looks like a great function. So does it exist? No. No. What? What's wrong with this function? Yeah, notice it's not of the right form. See, we have to be of the right form. You got to get y prime by itself. So you really should say y prime should be 4x minus 4 over y. And now you're like, oh, yeah, that's a problem. That's a problem. Because when y equals 0, you're dividing by 0. So what do we put? No's again. Ugh. Okay, the fifth root of y. Y of 2 equals 3. The fifth root of y, is that a continuous function? Yeah, it is. It kind of looks like the cubed root of y, but more fifth root-like, if that helps you visualize. If it doesn't help you visualize, it looks vaguely like this. That's the fifth root. All right. So that's a yes. What does the derivative of the fifth root of y look like? So if you take the derivative of y to the 1/5, what do you end up with? 1/5 y to the negative 4/5. Okay, now remember, y is near 3. Is that a continuous function near 3? Yeah. So is unique, yes or no? Yes. Okay, now here. Does this differential equation, does it exist? Yeah, we're continuous. It's a nice function. All right. Is it unique? Are we guaranteed unique? No. Because the derivative is bad. When you plug in 0, you're going to get 0 to a negative exponent. That's a division by 0. So there's an example of a yes and a no. This last one, xy prime equals 3y. Y of 0 equals 0. Exist? No. Why not? So you get y prime is 3y over x. No. That's a no. Now, let me ask you something. Let's look at this for a second here, because we've got like a minute. xy prime equals 3y. I claim there's a solution to that satisfies y of 0 equals 0. In fact, I claim there's a lot of them. Can anybody give me one? Sorry, what? Someone said something. Rhymes with eero. 0, okay. I claim 0 is a solution. Is it? Does 0 equal 0? Yes. Yeah, when you plug 0 into 0, do you get 0? Yes. How is there a solution when this says no? Wait a second, what's wrong here? So there's this word guaranteed. This background fact says, look, these are sufficient. But these are not if and only if statements. It does not say only if this is satisfied you have a solution. It says if this is satisfied you have a solution. So it's possible other things can happen. So that's why we're not claiming that there is no solution. We're just saying the fact doesn't guarantee us a solution. So that's why we see that no there. All right, and that's it for today.